Welcome to Hidden Layers, where we explore the people and technology behind artificial intelligence. I'm your host, Ron Green. Today on Hidden Layers, we're joined by Dr. Hannah Liu, assistant professor at the University of Texas at Austin and core faculty at the Odin Institute for Computational Engineering and Sciences. Dr. Liu is helping pioneer the use of AI to make complex simulations faster and more accurate. Her research blends scientific computing, reduced order modeling, and uncertainty quantification with machine learning to push the boundaries of what's possible in environmental fluid mechanics and Earth system modeling. Her work is building a new generation of tools for understanding our planet and making smarter, more informed decisions about the climate and the environment. All right, Hannah, thank you so much for joining us today.
Thanks for having me.
Okay, so you are at the University of Texas and you're pioneering the use of artificial intelligence, machine learning models to basically speed up simulations. And you've used this really successfully. And I'll link to the paper on the podcast, but you've used this to model sort of CO2 absorption geologically, and all the complexities around like fault lines and all the, very nonlinear complexity of geological deformations, etc. Historically, these types of simulations have been done using physics-based software where you have equations that theoretically capture the interactions of all the gases and solids, et cetera, but they're so expensive computationally, right? And so you've been exploring using artificial intelligence to speed that up computationally. Can you talk a little bit about why this problem is so difficult, why traditional methods are just so computationally expensive? And then I want to segue into your work on surrogate models.
Okay, that's great. So, like surrogate models, also sometimes we say reduced order models. They are simplified models for complex system, usually very expensive to simulate. For physics problem in science and engineering, we rely on partial differential equations, and simulating them are very time-consuming and super expensive. And thinking about even nowadays, we have more advanced computational capacity. It is still very challenging to simulate thousands, millions of them when you consider uncertain quantification, optimization, control problem. And in many applications, we have to make real-time decisions based on the model predictions, which cannot be supported by expensive traditional simulators. So there have been a variety of surrogate models, some of them looking for simplified physics, some of them looking for a projection from the high-dimensional space to the low-dimensional space. And with machine learning, deep neural network, we also have this deep learning-based surrogate models, which is trying to figure out the relationship between input-output in a physical system by leveraging the structure of the data from simulation or from experiments.
Okay, all right. So that's a perfect tee up. So surrogate modeling, which I'm relatively inexperienced with, so I'm pretty excited about this. Surrogate modeling. What is it at a high level? Like how is a surrogate model different from a traditional simulation? How is it trained? Why does it work? It seems almost like magic.
Yeah, so that's a good question. So first of all, it has to be much faster than traditional simulators. That's why you want to use it.
That's the main thing it's bringing to the table is speed, maybe?
Yeah, especially, as I mentioned, for the applications where you need thousands runs, millions runs for optimization for real-time applications.
Right.
Yes.
Okay. And so you have these surrogate models. It seems almost magical to me. You're saying, hey, we have this really expensive computer simulation using equations that we think accurately model some complicated process, but it's too expensive to run. So we're going to go with this other approach that's simpler, but you can still get accurate predictions. When these models are trained, how are they trained? Meaning, are they taking in exactly the same information that the traditional simulations would work with, performing a variant of the computations, or are they looking at like less data or like just key parts of the information that would go into a traditional simulation?
Yeah, so in the big picture, as you said, we actually have two phases for surrogate model. One phase is training. The other phase is using it for predictions. In the training phases, we first have to collect data from experiments or from high-fidelity simulations. So the data set usually consists of pairs of input-output.
Okay.
For example, the input can be a scenario where we want to reduce carbon emission by 30%, and the output can be what is the global temperature response in 10 years. And this input-output can be generated by very expensive global climate models. It can take days to simulate this kind of stuff. And after you train the neural network, which basically is solving an optimization problem of identify all of these hyperparameters in your network, which minimize the difference of your model output and the reference output. And after you train it, you can have a totally new input. Let's say we cannot afford 30% carbon reductions, but we can do 20% reductions. The model can predict what is the global temperature response corresponding to that, and then we can make decisions based on this kind of scenarios. So it allows us to explore different what-if scenarios and help us to quantify the uncertainties associated with it.
Okay, that helps a bunch. So when you're training the model, are you training it almost exclusively on the output from the more computationally expensive simulations?
Yeah, it depends on what is your interest of the problem. It can be it's basically learning relationship between the input and outputs. It can be a state-to-state regression problem. It can be a classification problem. It can also be a time series.
Right.
So it depends on how you define your input and output.
Okay, great. We've talked about Dr. Steve Brunton at the University of Washington. We both really love his work, and he's a big advocate of what he calls, physics-based machine learning or AI, where you essentially, instead of taking a model and letting it really sort of be unconstrained, let's say in the output space, you know certain relationships, or you understand the physics of the environment involved, and you can actually apply constraints to the model using known physical laws. My understanding is in your work, you didn't do anything like that, right? You guys left the model mostly unconstrained. Is that right, on its prediction? So does Steve work, does it impact your thinking? Like how are you thinking about the future of surrogate models? Are these two different paths, or do you think they're related a little bit?
Yeah, so I'm absolutely a fan of his work, his research, his YouTube channel, and the magic glass board.
He's so good. Exactly. Looks like he's riding backwards. It's amazing.
Yeah, I mean, actually, my PhD thesis on reduced-order modeling start with reading his book on dynamic model decomposition. And just this summer, I also passed the same book to one of my students. Steve Brunton, he's definitely an inspiration. So there have been a lot of work about how to use machine learning to physics problems appropriately. And of course, there are many ways. But we all know that machine learning arises from computer science, where, the application is more for image classification, where you have large amounts of data, but you don't have any physics or equations there.
Exactly.
But so it's true that nowadays we have more data than ever, but when it comes to complex physics problem, real life engineering problems, first of all, the data is always indirect. It's like I can get my heart rate measurement from my Apple Watch, but it is just an indirect measurement of the complex dynamics of my heart.
Right.
in earth science, we can also get pressure readings from a handful of wells. But the true dynamics of the subsurface is more high-dimensional and uncertain. And also, the data is always sparse in space and time. You do not want to live in a world where Earth is literally littered with sensors.
Right.
So the data is always sparse, noisy, indirect, and that has put a lot of challenge for classical machine learning. But luckily, we have centuries of studies in physics, like Newton's laws, conservation laws, and in different ways, we can use the help of these physics laws to help us construct surrogate models, which can work fairly well, but with relatively small data set.
Okay.
I think that is a goal, and there are different ways to do it, like using the PD as a penalty in the loss function, or building a library of possible terms in your equations that is more of the Cindy method developed by Stephen Brunton. And one of my previous work may be related to dynamic mode decomposition, which is a pure data-driven method. It doesn't work very well for a physical system with advection-dominated system. But when you combine it in the construction with the advection speed, which is a meaningful physical quantity in the system, when you incorporate this in the formulation of your surrogate model, it's super helpful in terms of improving accuracy and the interpretability.
Okay. What occurred to me right then was, if you're using a surrogate model on a system that is maybe like chaotic, where really small changes to the input could radically change the output, that seems to me like they would be a bad candidate, right? So are you seeing anybody using these surrogate models with chaotic systems, or is it more of a trend to avoid those for that very reason?
Yeah, that's a very good question. I mean, even without thinking about chaotic system, if just to think about the super nonlinear system, there has been a lot of challenges here. I think literaturely, there are many work in terms of quantify the error between a surrogate model, certain type of surrogate model, and their corresponding physics-based models. In this setting, everything can be written down precisely in equations. And I also had some previous work on this. We were able to do some mathematical analysis and derive some error bound for these systems. And we can even say something about when they are reliable, when they will not become reliable. But, for general system and for surrogate models, especially constructed by deep neural networks, it's very challenging to derive such kind of error bound and do this analysis, mostly because our theoretical understanding of deep learning is still under development.
Right.
So, but I think a more challenging and important thing is all of this framework assumes that the physics-based models is a ground truth,
Right.
which is often not the case in real life.
I would absolutely imagine in most cases it's not. Yes.
So because these physics-based models, they are themselves are approximations.
Right.
They rely on simplifications, approximations, and also they are inherent with uncertainties from like material properties, geometry, boundary initial conditions. So when you think about the issue of trust for models, for surrogate models, it's not only for surrogate models. It's actually the fact that we should be aware of all of the uncertainties comes with all models.
Right.
So, I think we should be very cautious in terms of using surrogate models and do comparison with high-fidelity simulations whenever you can,
Right.
and validate with experimental data whenever you can. But still, it's very helpful and meaningful if we can use the surrogate model to guide us investigate where will be the most informative region to do your next expensive simulation or expensive experiments,
Right.
so that we can test the boundary of our models.
Right. And let me say that back to you, make sure I understood all of that. We've got these surrogate models, which are taking in inputs that are actually the results of a more of a classical physics-based simulation. Those inputs, which are the outputs essentially of those classical physical-based models, may not be accurate themselves, right? They're roughly accurate. So you know it's almost like you're compressing something that's already been compressed in a way, right? But you can then go back and validate it against what happened in the real world as those simulations get better. Okay, so this is one of the big questions I was dying to ask you today, because I'm really blown away by these world models that are being created in AI right now. For example, the new VO3 model from Google, where you can prompt these visual video generation models, and they will produce output that is shockingly realistic. Right? I've seen examples of a prompt where it was like two old wooden ships in a coffee cup fighting a battle, right? Fighting a sea battle. And what's amazing about that is you see the waves, like the fluid dynamics look so accurate. And if you look at the light, it's almost like there's a ray tracing algorithm running, except for we know that none of that was put in. The model seemed to have learned some much more compressed way of computing outputs that at least seem realistic to us, right? I don't know if they are actually realistic, but visually they seem to work. My thought there is that essentially almost the same thing as the work that you're doing in surrogate models, where you're learning maybe a compressed manifold on which you can't simulate everything, but you can make predictions about the sort of the most important factors that you care about in that system.
Yeah, so you were talking about diffusion models and maybe more broadly speaking, generative models. They're definitely one of the most popular research topics nowadays. I think they are, the idea of compress the complex system, high-dimensional system, into something more smaller and faster to evaluate is quite aligned with surrogate model. And I think what makes diffusion model particularly exciting is that they are not only try to make one predictions for one point, but they are try to model the distributions.
Right.
So in principle, they can not only make one fast predictions, but also, for example, generating ensembles of different plausible scenarios and help us in these what-if questions and answering quantifications. But again, the question is, different from video generating. We cannot just generate a flow field that looks right, but violate physics laws like conservation of mass. So the question again is how to enforce or how to make these powerful generative models also respect all of these physical constraints. And I think that's a challenge and also the research opportunities out there.
All right. So a few more questions for you. This is so fascinating. So where do you see your work going in surrogate models? Like, do you think that this is really going to be it feels to me like core to simulations going forward. We're just having so much success on so many fronts, learning these more sort of compressed representations of these high-dimensional spaces and able to do so much more quickly. Are you really excited about the future here?
Yes, I am. I am personally especially interested in address all of the uncertainties comes with the surrogate model or existing physics models, and bridge the gap between whatever models we have and the reality, which we usually obtain by observations or measurement data. So it's like, I don't want to commit myself in finding the perfect model.
Right.
Because we have to embrace this idea that the model might fail sooner or later, or in different conditions. So instead, we should kind of develop a model that can adapt, can do improvement, with incoming more information about the system, with incoming more measurement data from the system. And so that we can make better predictions for the next step and make better decisions from that. I think this is where, this called model calibration comes in, and also very aligned with this new concept of digital twins.
Yeah.
It's really this bidirectional interaction between a virtual model and a physical asset is a key there to make higher fidelity of your model.
Right. Do you? There's a lot of interest right now in biology around digital twins. There are lots of companies out there trying to create, simulations of individual cells and things like that. I'm wondering about going the exact opposite direction. Like, is there much work being done in taking, for example, surrogate models and trying to derive formulas that are sort of lower dimensional representations of the system that are more computationally tractable? Mm-hmm. By that, I mean, obviously, these surrogate models are performing some type of computation, right? In the work in your paper, they're relatively small, fully connected neural networks. So it's essentially it's mostly linear algebra with some nonlinear functions. But I'm wondering if there's a way to take that and then derive a more efficient sort of analytic solution that you could then go drive the simulation. Does that make any sense? You sure I'm going with that?
Can you say more about it?
Yeah. Okay. What I'm imagining is we've got these physics-based simulations that are computationally really expensive. And then you've got the surrogate models, which are much, much more efficient. I wonder if there's a way to, once you have a surrogate model that is accurate enough, use it to essentially derive a better, more computationally efficient set of formulas that you could use for the simulation, and you wouldn't even need the surrogate model at that point.
I see your point. So that is more, I think, related to kind of quantity of interest driven learning. That is kind of that is a direction of sometimes discover maybe new physics there. That is also a fantastic area. Use the surrogate model, use a data-driven modeling tool as a way to discover the new physics there.
Yeah, discover the formulas that would allow you to represent it in a lower dimensional space, essentially.
Yeah, okay. That makes sense.
Okay, that's great. Can you show us an example of the simulations, what they look like? I know you've got some video of the computer simulations and then the outputs from the surrogate model itself.
Yeah, so in the left corner, you're seeing a video recording of an experiment that's done in Norway. My collaborators is just building this beautiful tank with layers of different geologies, like different layers of sand to mimic the geology formations. And they inject CO2 at designed locations. And this, as you can see, it's a super nonlinear system and with fairly complexity of the faults and geometry.
That is very complex.
And if you see there are some beautiful dissolution fingers, that is due to hydrodynamic instability. Okay. And of course, we have physics-based models. We have the equations to solve. In the middle, it is showing here But these equations comes with a lot of uncertain parameters. So here in the bottom, the blue lines is showing some ranges of the uncertain parameters. Here is just 3, but we have a lot of them in the system. So each combinations of them will give you very different solution profiles, can be very different from the experiments. Of course, there exists one of them within this range that can produce the simulation solution profile match with the experiments very well. And here is my collaborator, a real human, who identified this one combination in the parameter space that can produce this beautiful simulation that matches with the experimental results. But it takes so long for him.
It takes forever.
Each run is like hours to days to finish, and you have to run it multiple times so that you can match with the experimental data. So it's super tireful, super exhausting procedure. But then if we, use the simulation data and train a machine learning model, a surrogate, you can just within milliseconds, you can produce a fairly equivalent predictions and match with experimental results very well. But more importantly, we can use this cheap surrogate to help with us in this parameter identification procedure. And here you see these gray bars of histogram. It is not giving you one solution of the possible parameter combinations, but it gives you a distribution of the possible combinations. And some of them, as you see in the first figure, it is agreeing, the machine is agreeing very well with a human identified value, this red line here. But in some other cases, the machine learning is indicating some other possible solutions of the parameter combinations. So it will help us to explore, the other spaces, maybe higher values in the intervals here that can give you equivalently good match with the experimental data, or even better, we don't know that. So that just propose a lot of possibilities to explore the uncertain system and help us really understand this physical system.
Okay, that makes perfect sense. We'll link if you're watching this on video, you can see this. If you're listening to this, we'll link in the podcast to this image so that people can take a look at what we're talking about. Hannah, this was so awesome. Thank you so much for joining us today. I really appreciate it. This is fascinating.
Thank you, Ron, for having me here.
Thank you for listening to Hidden Layers. This series is hosted by Kung Fu AI, a management consulting and engineering firm focused exclusively on artificial intelligence. If you have any questions or thoughts about today's episode, or if you know someone we should feature, please visit us at kungfu.ai.